In this video, we're talking discrete random variables. Discrete meaning something that's countable, something like the number of cars in a drive-through. And the big what to, in this chapter, we're going to introduce distributions, a much cleaner functional approach to probability as opposed to this wild, wild west of picking and choosing various ways to calculate probability. Let's look at an example here. So one thing that we'll recall from the past is we talked a lot about this idea of center of data, which we often referred to as the mean was the best case. And we had two different characters to represent the center. We had this mu character and x bar. We'll talk about the difference between them in a minute. Again, center, we like to think of where most of our data is located. We were also interested in spread, this idea of, look, how wild is your data? We had a couple measurements for that, range, variance, but most importantly was standard deviation. We had two symbols for that. We had this upside down Q or sigma and S, two symbols to represent each. One center where most of our data is, and one is spread, how wild our data is. We'll get into those in a minute. I just want to recall them so they're fresh as we see some examples. So to introduce this concept of discrete random variables, and most importantly, if you look up top, probability distributions is this example here. Consider an experiment of flipping a coin 3 times and counting up just the number of heads when we flip them. That means there could be 0 heads, which would be all tails. There could be 1 head, 2 tails, 2 heads, and 3 heads. And this is what we're interested in coming up. Again, we're not interested in the number of tails, only interested in the number of heads. Well, in this number of heads variable, we're going to call it a random variable, where that random variable, sometimes you'll see it abbreviated RV, is x, and x could equal 0, 1, 2, or 3. And so to be really clear, whenever we talk about a random variable, the random variable is just one that its outcomes are probabilistic. They're random depending on what the experiment is. And so long as we can quantify them, at least in a discrete fashion, 0, 1, 2, 3, then we can talk about these different kinds of probabilities. And there's 2 distributions that we're going to talk about in chapter 4. The first one is a friendly one. But the reason we want to clean this up by talking about a random variable is because then our probability becomes a bit more straightforward. Let me show you an example. Say maybe I want to find the probability that you'll get 3 heads. That would be all heads, nothing else. Well, if you'll remember, we can write this as probability of x, this is our random variable, equal to 3. That refers to 3 heads. And if you want to go back to the basics, it's always the number that we want divided by our space. If we remember, if we flip a coin 3 times, in fact, I drew out the space for you just beneath me, that if I want all 3 heads, well, I have one of those. It's right here, all 3 heads. So 1 that I want divided by 8 as a decimal, that'll be 0.125, or you could think about this as 13% chance that success will occur. And so we want to clean up probability by referring to these random variables. My little example here is all heads. So let's see what these distributions can do and ultimately what they will look like. Slide over here. That's a little better. So we'll consider all these different random variables. For instance, the one that we just did, this was our 3 heads. The probability is 1 divided by 8. I'll leave it as a fraction for cleanliness sake. Well, I can fill in all these probabilities using our simple rules, right? The probability that I get 0 heads is also 1 divided by 8. There's 1 all tails divided by my space, and so on and so forth. For my random variable, 0, 1, 2, 3, and also the probability for each. This we'll call a probability distribution, or as I like to call them, these table distributions, because it's a table of different probabilities. Now, there's actually 2 very important properties that these tables possess. Here they are. The first one is just that all the probability of x equals little x is always between 0 and 1. This is the first property that all distributions should have. And this includes 0 and 1, right? The probability of something happening can be 0, never going to happen, and the probability can be 1, guaranteed. The second property, here's a little throwback for you. This character here, it's the Greek character sigma, capital sigma. Not that we need to know that. We should recognize this as the sum. If I sum up all the probabilities, it should equal 1, because 1 is everything in the whole wide world, and that's the second property. And so if we go up top, this table should have all those characteristics. Again, the probability, check, 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 is all between 0 and 1. Good, first property satisfied. The second property is if I sum them up, in this case, that's 1 divided by 8 plus 3 divided by 8 plus 3 divided by 8 plus 1 divided by 8. And yeah, that equals 8 over 8 or 1. And so all these two properties need to be satisfied in order to consider this a true probability distribution, or as we'll more fondly refer to them as table distributions. As a little note to self here, little recall for you, whenever we refer to a discrete random variable, those are usually counted versus continuous, which we'll talk about next time in chapter 5. These variables are usually measured. Something like temperature, for instance, can be a random variable, but those distributions look different than these table ones. Let's see an example of this table distribution. A child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X, our random variable, the number of times per week a newborn baby's crying wakes its mother after midnight. For this information, X can equal 0, didn't wake him up at all, 1, 2, 3, 4, and 5, meaning there are 6 different outcomes here, 6 different random variables, 0, 1, 2, 3, 4, 5, and all the different probabilities are computed for us. Find the probability that the mother selected at random wakes from her newborn baby crying once. And so pay attention to notation as we first kind of notate what we're interested in. This is like my random variable X is equal to 1. And so I'll write this as, they say, the probability. So I'll write probability of X equaling 1. And so I can write this here equals, and I can refer to my little chart. Here's X equals 1. So the probability associated with that random variable is 11 divided by 50. Or as a decimal, I can write that as 0.22 and box it. That's what the probability we're interested in. If you want to conceptualize that, you can think about that as 22%. That's the likelihood. Again, fairly likely when you consider all these different outcomes. It's almost a quarter of the probability. For the next one, probability, we're looking at more than 3. So X, my random variable, is, I'll write here, more than 3. Instead of me writing the word more than, though, we're going to do a little bit of inequality introduction here. But instead of me writing more than, I'll write greater than 3. A little shorthand for us to clean this up. So I'll write here my probability that X is more than, or I'll write greater than 3. And then I just need to look at my table and pick the probabilities that are associated with this outcome. So you might be tempted to say, oh, more than 3, but more than 3 does not include 3. Instead, I want more than 3, meaning 4 is good, that's what I want. And also 5 is what we want. And so a way I can translate this cumulative more than 3 is I can say this equals the probability that X is equal to 4, yes, plus the probability that X is equal to 5. Or maybe I can just jump right to these probabilities that for the first, it's 4 divided by 50, and then plus 1 divided by 50. If I add up those probabilities, I'll end up with 5 divided by 50, or as a proper decimal, that should be 0.1. You can box it. That's the probability we're interested in. If you want to convert that into a percent, you can. That looks like 10%. What's the probability that a mother's going to be woken more than 3 times? And more than 3, really all they're talking about is 4 and 5. Looks like 10% chance. Another inequality game that we'll play, the next one, between 2 and 4 inclusive. Now, whenever you read the word between, I'd encourage you to think of, look, that random variable X is literally between these two numbers, 4 and 2. To represent them with inequalities, I can say, look, I want X to be less than or smaller than 4, but I also want X to be greater than 2. Again, if I read that from right to left. Now, when we say inclusive, all that means is equal to. So let me write a little equal sign beneath these, and voila, we have exactly the inequality we're interested in. I'll write this as the probability that 2 is less than or equal to X is less than or equal to 4. That X is between these two values. Now, just like we did up top, it's important to understand what this event is asking us for. So we'll refer to the table and we'll simply pick these values. So we're interested in it being between 2 and 4 inclusive. So we do want 2, I do want 3, and I do want 4 as well. This is what I want. And so I'll write my probability as a probability. Instead of writing X equals, I'll just write 2 for short, plus the probability of 3, plus the probability of 4. So now I have all of my values. I can look up top and refer to their probabilities for each. For the probability of 2, that's going to equal the 23 divided by 50 plus the probability of 3, less likely, 9 divided by 50 plus the probability of 4, even less likely, 4 divided by 50. I can add all those up, no problem. 23 plus 9 is 32, plus 4 is 36 divided by 50. 36 divided by 50, do I want to put that in a decimal? I can. I'll get 0.72, and that's the decimal answer we're looking for. As a percentage, let me make sure I'm out of the way here, it should be 72%. That's fairly likely. And so, again, maybe if we're getting woken between 2 and 4, well, actually it looks like we're in a good majority there. 72% of women, mothers, are experiencing the exact same thing. So this is how we read or pull information from a probability distribution. Again, much more friendly than having to compute each one by hand. Instead, now we're just pulling information, reading it from a table. It's also important to understand how to discern whether these probability distributions are actually even proper probability distributions. Let's look at an example figuring out how to discern whether or not they are. For each of the following tables, determine whether the table represents a discrete probability distribution, which again is just these fancy table distributions. Indicate your answer by circling yes or no, and make sure to justify your response, right? Why are we saying yes or no? We're also going to do a little bit of Excel. I'll get to that in a minute. For the first one, I want us to recall what are the two things that all probability distributions should have. The first one was just that all the probabilities have to be between 0 and 1. All my probabilities, right? They need to be actual make sense probabilities. And this is something we can check on our list. For the first one, this is 0.1 or 10%. Yeah, that's golden. That's a probability we can talk about. 0.3 or 30%. Yep, that's also a good probability. 0.05, that's 5%. Yeah, that's probability. 10%, also good probability. That's 15%. Yep. All these make sense for probabilities. They're all between 0 and, wait, look at this, negative 0.2. Somehow this is talking about like negative 20% chance. No, definitely can't have that. It fails that first rule. This is not a probability distribution. Fails that first checkpoint. The second one refers to the second check that we need to perform is that the sum of all my probabilities, I'll write this capital sigma here, for sum of all my probabilities has to equal 1. And so these are the two checks that I need to perform. For the second distribution, let me pull up Excel. Of course, you could do this by hand pretty quickly, but Excel does it a bit quicker. So let me demonstrate that for you here. All righty, here we are. I have our tables up above. I have Excel pulled up down here. Let me refer to my tables and I can just copy and paste this information. So I'll hit Control C, go over to Excel anywhere I want, and hit Control V and paste my information into here. If I remember, those two properties are as follows. The first one was just that all my probability had to be between 0 and 1. I can look at my list, my probability of 0.2, I can look at that as 20%. Yeah, golden. Check on there. All right, W for win. Nice. All right, 0.2, W, fine. 0.1, yes. 0.1, also good. 0.15, yes, good. 0.2, yes, good. And 0.05. All these certainly pass. Flying colors, check, or golden in that regard. The second property just says that the sum of all my probabilities should equal 1. Fortunately for us, we have a very quick way to do this, and I have a function for that. Again, sum, there is actually a sum function. Make sure you type in equals, and then you type out sum, and you'll see right there, it'll sum. Either you can double click or you can hit the tab button, and it'll finish it for you. It says, look, what would you like to sum up? I can simply go hover over, and I can select, click and drag all of my different cells all the way from B2 to H2. Let me copy that over so we have it for reference. And there it is. The sum of all my values is equal to 1. Another big, I'll write it here, check. Satisfies both of those conditions, no problem. I think I can fill it in here on our notes for reference. Yep. Yes. First condition and second condition, both satisfied. Beautiful for us, buoy for us. What about the second probability distribution? Let's check it out. So again, I'll copy my data over. I think we can fit it right down here. I'll paste my information here. So here's my second probability distribution. I can look at all my inputs just like we did before, and they certainly pass the first check, where again, all my probabilities are between 0 and 1. I'll write a big check here. Yes, they're all looking good in that regard. The second check, again, is that the sum of my probabilities should equal 1. Fortunately for us, a quick check. If you want to, you can type in equal sum. There's also a very fancy way to do this as well. Excel kind of anticipates different calculations. And if you simply select the cells that you have, let me see, I might have to move out of the way here. There we go. It'll tell you the count down here below. It'll also tell you, look at that, the sum. And it'll tell you this sum right there is 0.95, just to demonstrate equal sum. I'll use the arrow keys and hold shift and select. And just like that, I will get a sum of 0.95. That is a big no-no, fail. Definitely did not work for us. Again, that little trick is simply selecting those. And down at the bottom, you'll see the count, you'll see an average, and also the sum, very common calculations that are performed. And so failure, this is not a proper probability distribution. No. And justify, why did we say that? First one passed just fine, but the second one, the sum of all of my probabilities did not equal 1. In fact, when I sum them up, I'll write it like this: the sum of my probabilities was equal to 0.95. All right. Failure in the highest degree, not probability distributions. And so again, this probability distribution actually means something for us, that we need to have these two criteria satisfied. You can check them by hand if you like. You can also use Excel, and that's hopefully what I demonstrated in this example. Let's look at the next one. So we talk about these different distributions. We can read probability, and we can also verify that they are proper probability distributions. But when we first started talking, we introduced this idea of mean, center, and standard deviation or spread. How do those relate to these different distributions? Let me give you an example. To show this, let's refer back to our coin flipping example. We flipped a coin 3 times, and these were the different responses: all heads, heads, tails, and so on. You remember there was a space of 8, and equaled 8 different outcomes. But let's explore, maybe there's some winning involved. Let's say you win $3 if you get all heads or all tails. And so instead of me talking about X, the number of heads, now I'm talking about W, number of winnings. So there's only 2 outcomes for W. The probability W equals 3 is, well, there are 2 winnings out of the total of 8, or 1 divided by 4, or as a fraction, as a decimal, I'm sorry, that's 0.25. There's a 25% chance, if we play this game, that we'll win $3. Interesting. Otherwise, we walk away with nothing, meaning that that random variable is $0. What's the likelihood there? Well, there are 6 non-winning outcomes out of the 8, or as a fraction, decimal, that's 0.75. Or I can write that as 75%. 75% chance that we won't win anything. And so how can we think about this as, what do I expect is going to happen? Notice we can expect to win $3 every 4th game. This idea of every 4th game, think about lining these games up, and it's like, out of 4 games, I'll win $3. I can actually write this as a fraction. I can write this as, look, I'll win $3 every 4 games. So if I want to reduce this fraction, right, what is 3 divided by 4? I can write this as $0.75 per 1 game. And again, to get that 0.75, all I did was 3 divided by 4, and I got the 0.75. So that got rid of the idea there of 4 games. And so let me write this then. What do I expect is going to happen? Well, I expect for every game I play to make $0.75 or 75 cents per game. Oftentimes, especially if you're in a physics class or what have you, anytime you see a fraction, you think of that as per. How many times does it happen per game? 75 cents. So how do we relate that to these probability distributions? How can we think about this? This word expected actually has a very close tie with the idea of a mean. What's the center? Here's how we can answer that question. What is the long-term or average mean winnings from the experiment presented above? In other words, what would you expect the average earnings to be? There's actually a formula that I'll show you shortly, but the formula looks something like this. It's a game of multiplying 3 times 0.25. If you multiply those together, you'll get 0.75. And then if you multiply the next category, which is $0, you'll end up with, go figure, $0 here. And if you add those two together, you'll actually get your average 0.75, which is exactly what we got using our verbal arguments here. So what is the expected or the average earnings? I can write this as mu is equal to 0.75 dollars. And again, this is dollars if I want to give it some context per game. This is where the applications come in. Again, I'll give you guys a formula in a minute, but this is where we can use this. Because again, I'm never going to play this game and actually win 75 cents. In fact, it's impossible. I'm either going to win $3 or no dollars. There's nothing in between. But when we think about playing this game over and over and over, this is what I win every game. Remember that $3 per 4 games. So let's say we play 412 games. How much can you expect to win or lose? We're going to do a little bit of fraction unit cancellation, if you will. So I have the number of games, and then I can multiply that by my dollars per my number of games. In fact, I can look at this, the dollars per games, that's exactly the mean. I can multiply this by the number of games times my average or my expected earnings. So this is going to equal 412 times that 0.75. And to give this thing some units, that 412 represented games. Over here, this 75 cents is dollars divided by games. And so these games are going to cancel, and we're left just with clean earnings here. 412 times 0.75 gives you an answer of 309. And this is dollars. We're not talking games no more. How much do I expect to win? $309, which is possible by winning as many games, $3 at a time. And so this is where we use this idea of expected average, this long-term average, that not any one game will I earn 75 cents, but it's over the long term. As I continue to play, this is what I can expect to happen. Let's look at that formula that I mentioned earlier. So this idea, mean, expected, these two things go hand in hand. They are synonymous. That being said, we primarily stick with this term of expected value. You'll see why in a couple examples, that the expected value is this long-term average. And the formula looks like this, that the mean, or the expected value of the random variable, is equal to some characters here. I'd encourage you to think about and write what these characters represent. This is the sum of x, that's your random variable, times p of x, that's your probability. And we're just summing all those up. So we have all of our probabilities. We're going to multiply, add, multiply, add, multiply, add, and so on down the line. The variance follows a similar formula, but it's a bit kooky because there's two different versions. Let me highlight which one is more important. Again, the variance is a means to an end. This is a measurement of spread, but the variance, something like sigma squared, only gets you to the standard deviation. The standard deviation is primarily what we're interested in. I'll show you an example later. But for the variance, sigma squared, or sometimes written just variance of x, our random variable, there's this formula here. You can read it if you'd like, but let me highlight a more friendly formula, one that we'll use in a minute. And it looks like this, that I want to sum up x, that's my random variable, squared, times p of x, which is probability. After you sum up all that, then minus the mean quantity squared. This formula is more friendly and it's much easier to compute. It's also very similar, if you look up top, to the mean formula, x times p of x, x squared times p of x. We just need to keep on that added step at the end to minus the mean squared. And this is how we can compute the variance. The beauty of it, once you have the variance, you can compute the standard deviation, which is often what we want to measure spread. It's the standard deviation, and you can typically just take the square root of the variance. Let me slide over here so we can see these formulas a bit better, at least how we'll see them on a little cheat sheet here. Now look, for this particular distribution, probability distributions, I'd encourage you to think of these as table distributions. We have a mean formula. Yes, x times p of x, sum it all up. And for variance, I have x squared times p of x, sum it all up, and then afterwards subtract the mean. So there's the formulas written for us. Suppose Nancy has classes 3 days a week. That would be like Monday, Wednesday, and Friday. From her past semester, she's confident she attends all 3 days about 80% of the time, 2 days, 15% of the time, that's missing one class, And one day, 3% of the time, it's missing 2 days from the week. The results are compiled in the table below. And so here's our random variable. This is how many days she attends. So 1 day, 2 day, and 3 day, those probabilities were given to us. But the problem is, if we read up top, the question never states what's the probability that she attends 0 days, that she misses the whole week. We can actually figure that out using this table. If you'll recall, all these probabilities have to add up to 1. And so to find k, I just need to find out that missing chunk. I can write here that k plus 0.03 plus 0.15, that's 15%, plus 0.8, 80%, it should equal 1 or 100%. If I add up my miscellaneous probabilities, I'll end up with k plus 0.98 is equal to 1. And so to find out what k is, let me just subtract minus 0.98 from both sides. And I should end up with k is equal to 0.02. There's a 2% chance that she does not attend at all, and she's absent from all 3 classes. So let me fill that in on our table. 0.02. Now we have a proper probability distribution. Now we can answer the questions. Actually, they're over here. On a given week, find the expected number of classes Nancy visits. What do I expect to happen? Anytime you hear expected, I'd encourage you to think, hey, I know what that is. That's just the mean. So the first thing I'd encourage you to do is write out the formula, and then we'll do it by hand. You can also use Excel. I'll show that in the next example. Looking back, I have this formula. The mean is equal to sum of x times p of x. And then I can actually write out what that sum would be. Again, x times p of x. If it helps on your table, think of multiplying these two together and getting that result, and then adding it to the next multiplication, and then adding it to so on down the line. So for the first one, I should write 0 times 0.02, and that represents x times p of x, for x being 0. For the next one, I have 1 times 0.03. Again, that's x times p of x plus. And we could keep going. We could go 20 columns long, but fortunately, we only have the 4. Next up, I have 2 times 0.15 plus 3 times 0.8. And these are all my columns placed here. So I can multiply these together. The first one's always the most friendly. 0 times, no problem, 0. And then I have plus 1 times, that's going to be 0.03. Next up, plus 2 times 0.15 is going to be 0.3. And lastly, 3 times 0.8 is going to be 2.4. If I add these up together, we can do so pretty friendly. I should get an average of 2.73. And that's my average. This is the number of days we expect her to attend each week. 2.73. Pretty good average. But how can we apply that average? Let me swing out of the way here. There are typically 14 weeks in the semester. If you ignore holidays, that provides, let me get out of the way here, 14 times 3, meaning there are 42 days of classes. For an upcoming semester, how many days of class is Nancy expected to miss? There's a couple different ways to do this. Let me start with this way. How many do we expect her to attend? Expect to attend. Out of the 14 weeks, well, I know she's expected every week to attend 2.74. So why don't I multiply those two together? That's 14 weeks times 2.73 should give me a number like 38.22 is how many days in total, number of days to attend. That's how much we expect her to attend. And so if I swing out of the way, 42 days in total, then I know how many she'll miss. She will miss 42 minus this 38.22, giving us, if we ignore those 0.22 that she maybe attend 22% of the class, ignore that, we should get 4 days that we expect her to miss. Expect to miss. And so this is how we can answer questions like this. And so, especially from a teacher's perspective, it's friendly to put all this information together. We can look at a huge roster, a couple semesters maybe, and I can say, look, this is the average number of days that student missed. And maybe that'll inform the policy and say, look, if you miss the average number of days, no big deal. Anything beyond that, well, maybe there's penalties. But 4 days expected to miss, using the number of attended expected mean and subtracting it from the number of total days. This one's going to involve Excel. A quiz is worth 5 points is given to a statistics class. Let X, the random variable, represent the score of each randomly selected student. The distribution of X is given below. So this is them winning or getting 0 out of the 5 points, 1 point, 2 point, 3 point, 4 point, and lastly 5 points. Confirm that the average is 3.03, so we'll confirm that in a moment, to then later find the variance of scores using Excel. And so here's my little distribution. Let me pull out of this presentation mode to then show you how to compute the average. Here I have Excel embedded, and it should look something like this. And so again, this is exactly Excel. It's just kind of embedded into our PowerPoint slide. So I've already copied and pasted our data. Probably that they get a 0 on the quiz. It looks like there's a 5% chance. And the first thing I want to do is calculate the mean. If you remember the formula for the mean, it looked like this. It was the sum of X times P of X. That was the little formula that we were interested in. Now, if I want to figure this out, I can simply, like we did by hand, I could write 0 times 0.05. If you're wondering why it's not computing, make sure you write the equal sign beforehand. And then, yeah, it'll get that calculation for me, 0. But this is very arduous, especially if I had to type this out equals every time, equals 1 times. Instead, let me use cell referencing. Let me write equals, and I'll click on, this is D1 for me, times probability, 0.12. And so again, you might be looking at that saying, okay, what's the point of cell referencing? That's maybe not necessarily saving you some time. Let me show you a very friendly trick here. Again, I could go over here and I could write equals and I could click, multiply, click. Or what I can do instead is once you type out that notion, D1 times D2, I can find that black cross here in the corner. You can see right there, I found it. Click that and drag over, and it's going, oh, I know what you want me to do. I want you to move over those references. And look at that, if I double click here, it'll move over those references all the same. So if I find that black cross here again and pull, there we go, it'll make that references for all these. And so it's very quickly to multiply them together. Nice little trick there, if you will. Find that black cross here and drag. So here I have all the X times P of X quantities. If I want to find the sum, no problem, equals sum of my reference here. I'm just using the arrow key, then holding shift and selecting all of my different multiplications that I want to sum up. So here I have it here. Let me write this, boop, that this is the mean below, 3.03. So yeah, we confirmed it up above. Confirm the mean is 3.03. Done. You got it. Find the variance. I've typed up the formula for the variance up top, so I won't type it here. But for the variance, it's very similar. I need to first have the sum of X squared times P of X. And so I'll do the same steps we did before, where I'll use cell reference. I'll write equals X. In order to square things, you can use the little caret symbol. It's shift 6 to write the caret symbol. I want to square it. So that's X squared times probability. I can just click it, C1 raised to the squared times C2. I can type in equals, and it'll say, oh, look, I gotcha. 0, of course. And then I can find that black crosshair like we did before, and it'll square and multiply all these different quantities together. Notice if I bring this one further, it's going to be like, I don't know what you're talking about because you're asking me to square things that I cannot multiply. So I have all of my X squared times P of X. So just like I did up top, I'm going to write equals. I'm going to sum up these X squareds times P of X, and I'll get my sum here. Write this for reference. There's my sum. If I want to then get my final value, it's a bit strange, but I'll write it here. My variance is going to equal that sum that I had before, this sum, or you can just type it out if you'd like to, 11.23 minus my mean, 3.03, quantity squared. And I'll type it out mostly for reference later. I think it's more friendly to have this typed up. And we have our variance, where it's the sum, 11.23, minus the mean, 3.03, quantity squared. If you want to be more precise, you can use cell references instead of typing those values. I finally get my variance, or my sigma squared business, is 2.0491, or if you can simply copy and paste the value that we calculated before. There it was, there's our variance. So what can you do with variance? Again, variance is a measure of spread, how wild your data is. So maybe we could compare different tests or different quizzes in this case and compare their spread, and maybe that would tell us something about either the students or the test that we're creating. Another thing we can do is we can look at probability. Let me look at an example. If this is just the standard deviation is equal to 1.43, what is the probability of a student earning one standard deviation above the mean? Okay, so they're saying something about probability, meaning I'll need something to do with probability that X. Let's see if we can understand what they mean when they say one standard deviation above the mean. These things have meanings. Let's talk about them. So one standard deviation, I can write that. That's 1 times a standard deviation, or sigma. And then above, meaning I want to add that to the mean. So this is just a very fancy way, earning one standard deviation above the mean, one standard deviation plus the mean above. It's going to equal then 1 times the standard deviation they said was 1.43 plus the mean. We have it up top, 3.03. If I add those two values together, no problem, I should get 4.46. That's my one standard deviation above the mean. So now if we go back and read the example, we're talking about a probability of the student earning above this particular score. Again, above, I can think of that instead as greater than. Probability X is greater than 4.46. I think one of the most difficult parts about this particular probability is simply understanding what the value we're comparing it to. But once we have it in this form, I'm looking for values of X that are greater than 4.06. If I look up top at my table, you can see I'm looking for X, my random variable being greater than 4.6. It looks like this is the only outcome that I want. And so really, the probability that if a student earns one standard deviation above the mean is the exact same thing as just saying, what's the probability that X equals 5? That is a perfect score on this quiz. Well, we can look up top pole from the table, 0.17, or from a percent idea, that's a 17% chance. What's the probability? I can tell you, 17% chance. Not super likely that somebody will get a perfect score, or as the example states, one standard deviation above the mean. We'll look at later, and it refers to empirical rule, why we're interested in one standard deviation below, one standard deviation above the mean. Chad is trying to decide between two different investment opportunities. The two plans are summarized in the table. The left column is a plan which gives potential earnings each month, and the right column gives their prospective probabilities. And so this month may earn 1,350. What's the probability that occurs? About a 10% chance. And that's how you read this table. And there are two separate plans to choose from. Let's say an analyst computes these values that we have a mean for the first plan of 270 and a standard deviation. Again, that's a measurement of how wild my data is, versus my second plan, which has a mean or expected value of $320 and a standard deviation of $862. That's the measurement of how wild this information is. So there's two different investment opportunities. How do we choose between the two? It actually depends on what we want. For instance, part A, he wants a higher payout in the long term. This higher payout means, hey, look, I'm in it for the long haul. I'll hold as long as I need to hold. I want the most money. Well, that means on the long term, I want to get a maximum expected value. Whenever you hear expected value, it should be sending some bells off. Expected value just refers to a mean. So this idea, if he wants a higher payout in the long term, means we want a higher mean. And if we're looking at higher means, 270 for my first plan versus my 320 for my plan B. Okay, this choice would be obvious. If we're just trying to maximize a higher payout, then we should certainly choose plan B because of the expected return or value in this case. But what if we're more risk averse? Okay, maybe we don't have 30 years to put our money into an account and keep reaping rewards after those 30-year period. Maybe I want to avoid risk. What should he invest in? Well, my little hint here is we think about variability here. Again, I don't want to have a lot of fluctuation. If I do have movements, I want maybe smaller gains, smaller losses, right? We think of avoiding risk. We think of having less wild data, less wild I'll write here a smaller standard deviation. Yep. So I have my two values that I can compare. For the first, I had 637. That was the spread, how wild my data was for plan A, versus my second was 862 for plan B. So although plan B might, over the long term, earn more money, there's certainly more risk associated with it, right? More fluctuation. And so if I want to avoid risk, let me pick the one with less variability. Plan A is the one to go. And this is oftentimes how big plans are picked, that we look between two. And oftentimes, especially depending on how you're building a portfolio, we're not going to just pick one or the other. It's like 80% higher payouts and then 20% avoid risk. Not really, but that's a good idea depending on your age or when you start investing, how these things are built, depending on what your priorities are. But how do we look at this as, for instance, like a probability? We want to understand what the likelihood of these events occurring. Over the course of many months, we can be 68% certain that the earnings will fall within one standard deviation of the mean. And where do we get this? It's from the empirical rule that we've talked about in the past. Here's a little chart for your reference here, recall. So if we think about that, if 68% is in the middle, and let me write on this little chart here, this is, again, the most likely 68%. If I zoom in the bottom here, you can see that that's minus one standard deviation, plus one standard deviation. 68% is in between. So then if I think about, okay, let's look at those opposite ends, that I have this idea that it's actually possible for me to earn below that one standard deviation. It's also possible for me to earn above, but I'm interested in that below. So if I think about that, 100% minus 68, so that gives me what's left on the two sides. There is 16% below and 16% above. There's a 60% chance that those monthly earnings will fall one standard deviation below the mean. My head's barely in the way. What are the earnings of each plan if this occurs? What are the earnings? So how can I write that one standard deviation below the mean? Well, I have the mean sitting right here, and I want to go below that, minus one standard deviation. One standard deviation below, subtract, take away from the mean. And I want to do that for each plan. I can do that. Here we go. For the first plan, I'll write plan A over here. I have the mean of that plan was $270 minus one standard deviation. That's 637. If I subtract that, we're coming in the negative. That's not good. I'll end up with minus 367. And this is dollar bills. We're losing money on that plan A. If I switch over to plan B, I have the mean, which was 320. Again, higher expected value, but then I also have a higher standard deviation, 862. I can subtract that and I'll get minus 542 dollar bills. And so again, we often think about, to help us conceptualize this idea of higher payout, yes, there's a higher expected earnings every month, but it's possible, in fact, there's a 16% chance that on any given month that I could lose either $367, okay, so certainly a fair amount, especially every month. Or if I took the riskier, the higher payout, it's possible that I could lose 540. And so more losses. But the beauty is, again, on average, I will make more money on plan B. And so again, with these investment strategies, it's very important that we understand this balancing act between, okay, look, am I holding in for the long term, or am I going to sell everything early? Alrighty, let me try to wrap or recap with this. We have these different distributions that look, instead of being so focused on how do we calculate probability of a single event, we're much more interested in a bigger picture to say something like, how do we calculate probability of a bunch of different events occurring? And instead of trying to figure out how all these different rules apply, once we figure out what distribution we're in this case, probability distributions or table distributions, as we like to call them, we can simply find probability by adding up our probabilities. It's much more friendly to compute probability. But with that convenience comes other things like calculating the mean and standard deviation that we have as well. And so it's important. This is our first distribution that we'll talk about. In the future, we'll have more distributions. In fact, in total, for the basic statistics, we'll have 4, kind of 6, depending on your perspective. And so it's important that we understand these criteria. In this case, very friendly. If you have a table, you're going to have a probability distribution and how to compute them. If you liked the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.